Hi, my name is Danielle Griffith, and the title of my tutorial is Fundamentals of Frequency References. If you have any questions after watching this tutorial, please join the live question and answer session on February 19th. First, I will start with a short introduction of myself. I received my bachelor's and master's degrees from the Massachusetts Institute of Technology, and I'm currently a fellow at Texas Instruments in Dallas, Texas, in the Low Power Connectivity Business Unit, focusing on efficient wireless systems. I've been involved with the IEEE and the Solid State Circuit Society throughout my career, including publishing multiple papers and a book chapter, giving frequent workshops, serving on technical program committees for the last 10 years. And I've also been an SSCS Distinguished Lecturer and Associate Editor of the Journal of Solid State Circuits. The outline of this tutorial is as follows. We'll start with the motivation and then look at the key metrics and the frequency reference landscape. Then the majority of the tutorial will be focused on the different types of frequency references. I'll talk about them in order of increasing accuracy, starting with fully integrated silicon references, then moving on to discrete or multi-chip frequency references, which will include ceramic, MEMS, and crystal oscillators, followed by temperature-compensated crystal oscillators, oven-compensated crystal oscillators, and finally end with chip-scale atomic clocks. After this summary and conclusions, I will suggest some relevant papers to you that you should be sure to see at ISSCC this year. Finally, at the end of the tutorial, there's a list of key references to read if you'd like to learn more about any of these topics. Now let's start with the motivation. So why do we care about frequency references? Simply put, nearly all electronic systems around us need at least one. 5G, the Internet of Things, infrastructure, consumer, automotive, and industrial electronics are just a few examples. However, the frequency reference accuracy requirements vary tremendously across the different applications. For example, a microcontroller clock may only need to be accurate to plus minus 1%, which is 1 second in 1.7 minutes. However, a USB interface for data transfer requires clock accuracy of 500 parts per million, or ppm, which is 1 second out of 33 minutes. A wireless node used in a factory for machine health monitoring probably needs an accuracy of 20 parts per million, which is 1 second in 14 hours. Finally, if we consider NASA's Deep Space Atomic Clock, it is accurate to 3 times 10 to the minus 9 parts per million, which is 1 second in 10 million years. So you can see that even though the frequency references are everywhere, their requirements can vary by many orders of magnitude. So humans have long needed a way to keep track of time. The calendar was invented at least 5,000 years ago, giving a timekeeping accuracy of 1 day. The sundial was first used around 1500 BC, giving a timekeeping accuracy of better than 1 hour. In 1283, the weight-driven mechanical clock gave an accuracy of around 30 minutes per day. And by the late 1600s, the balance spring or balance wheel had been invented, which was accurate to around 10 seconds per day. Just over 100 years ago, the first quartz crystal oscillator was built, giving an enormous improvement in timekeeping accuracy, taking us to 200 seconds per year. Since then, we've seen 9 orders of magnitude improvement in the accuracy in the last century, which has enabled the technology we take for granted today, including high data rate communication, accurate GPS, and other applications that fill our everyday lives. Now let's discuss some key metrics for frequency references. The first key metric is frequency accuracy. This means simply how close the reference frequency is to the ideal value. The second metric is frequency stability, which can be quantified over both short and long time periods. For example, in the top graph, you can see an example plot of the frequency versus time. Here, the instantaneous frequency shifts from one clock cycle to the next around an average value. The frequency variation is quantified by the phase noise or jitter metrics, where the jitter is the deviation in the timing relative to the ideal value. There are many types of jitter metrics, including period jitter, cycle-to-cycle jitter, integrated jitter, and accumulated jitter. Which one is most relevant depends on the application. Next, The middle plot shows a two-sample or Allen deviation measurement. Here, the shift in the average frequency is measured over an observation window tau. You can see that the results would be different for this curve depending on the length of the measurement window. Finally, frequency references all experience some amount of frequency shift, also called aging, as shown in the bottom plot. This frequency drift will occur over hours, days, or even years of operation. In addition to frequency accuracy and stability, another important metric is the target frequency. Most frequency references are in the range of kilohertz to gigahertz. Many frequency references also have a specified tuning range, which allows the frequency to be adjusted to meet the application requirements and to compensate any frequency shift due to environmental changes, as shown in the figure to the right. Here, the frequency is plotted versus a tuning code for 3 different temperatures. In this case, the tuning code could be adjusted to get a constant frequency versus temperature if the application required it. Another important parameter is the power consumption, which is usually higher for references with better stability. Next, the startup and stabilization time are important for duty cycled applications. This can be less than a microsecond for high-frequency oscillators to more than an hour for an OCXO or an atomic clock. Finally, a frequency reference needs to provide a stable frequency even when the surrounding environment changes. So far, we have seen examples where the frequency changes versus time due to circuit aging and also due to temperature as shown in that example tuning curve on the previous slide. However, the reference frequency can also be impacted by changes in the load, the supply voltage, or the bias currents. If it's operating in a harsh environment, such as a car or a factory, it could be impacted by acceleration, vibration, or shock. An example of this is shown to the right, where the frequency curve, the frequency shift versus time is plotted for 2 different oscillators. A shock occurs at the first black arrow, and then the oscillator shown by the red curve has a 7 ppm frequency shift in response to the shock, while the oscillator shown in the blue shows only a 2 ppm shift in frequency. On a longer time scale, the frequency can be impacted by changes in stress, strain, humidity, pressure, gas permeation, radiation, and so on. As you can see, the list of potential sources of frequency inaccuracy is really quite long. So now with that introduction, let's look at the frequency reference landscape. On this slide, the frequency stability in parts per million is plotted versus power dissipated in watts. The different types of oscillators shown here will each be discussed in more detail throughout this tutorial. To the upper right, we have the oscillators which are entirely integrated in silicon, usually accurate to about 0.1% to 10% and consuming microwatts of power. Next, increasing in accuracy and power, we have ceramic oscillators, then crystal and MEMS oscillators, followed by TCXOs, or temperature compensated crystal oscillators, which are accurate to a few ppm but consume closer to 1 milliwatt of power. Continuing on, we find OCXOs, or oven compensated crystal oscillators, which have stability measured in parts per billion, or ppb, which is 1 e to the minus 3 parts per million, but they consume closer to 1 watt of power. In the bottom right of the plot, we find the rubidium and the cesium atomic clocks, which are several orders of magnitude more stable than the OCXOs, but they also consume much more power. On this slide, some typical electronic applications are shown on top of the different types of frequency references. First, in the upper left, we see the microcontrollers and USB, both of which were mentioned in the introduction. They require clocks with relatively relaxed frequency accuracy, so they can be implemented with integrated oscillators or ceramic or lower performance crystal oscillators. Next, we see utility meters, which often require both accuracy in the range of 10 to 100 ppm, but still having very low power consumption so that the meter can enable accurate billing while being battery operated for many years at a time. This is implemented with low power 32 kilohertz crystal oscillators. Next, we see many wireless standards, such as Bluetooth, Wi-Fi, and cellular, which require accuracy in the range of 5 to 50 ppm, but they can support slightly higher power consumption that this accuracy requires. These standards typically use crystal and MEMS oscillators or TCXOs. The next example is test equipment and base stations, which require significantly better accuracy, this time in the range of parts per billion. These applications may use OCXOs, which are oven-compensated crystal oscillators. Finally, applications that require accuracy that can only be achieved by atomic clocks include aviation, radar, satellites, space, military, and seismology. Now we're going to move on and talk about the different categories of frequency references, going from the top left of that chart on the previous slide towards the bottom right. In other words, in order from lowest accuracy to highest accuracy. The first category of frequency references are those that are fully integrated in silicon. So how do we make an integrated oscillator in CMOS? The most obvious candidate to make a low power oscillator is a ring of cascaded inverters. As a ballpark number, you get roughly 50 nanowatt per megahertz per gate for a 180 nanometer technology node, and this decreases with technology node, so this is promising for a low power design. However, the frequency variation is large. On the right there is a simulation showing the frequency of a ring oscillator simulated over 3 process corners, 3 supply voltages, and from -40 to 85 degrees C. We see a 2x variation with temperature, a 3x variation with process, and a 5x variation with supply. This is far above the target of 1 to 2% maximum frequency variation. So how do we make this more stable? Well, one way to make a more stable integrated oscillator is to design a relaxation oscillator. This is an open loop architecture as shown in the figure to the right. In this circuit, a current charges a capacitor. When the capacitor voltage reaches a reference voltage set by a current into a resistor, a comparator resets the capacitor voltage. This gives a frequency proportional to 1 over RC, which means that the frequency is dependent only on the values of R and C to the first order. However, because the resistor and capacitor are on chip, they will typically vary by 20% due to the silicon manufacturing tolerances. This means that at the very least, this architecture requires the frequency to be trimmed during production to have a frequency that's sufficiently accurate. Even with a one-time frequency trim, the accuracy of this oscillator is limited by several factors. First, the resistance and the capacitance will vary as the temperature changes. The temperature coefficient can be between 50 parts per million per degree C up to 3,000 parts per million per degree C. This means that just this error source can cause between 0.5% and 30% frequency variation over the industrial temperature range. Not only can the frequency vary due to the R and the C, but also due to changes in supply voltage, offset and delay variation in the comparator, and the mismatch in the current sources charging the resistor and capacitor. So what can we do about these error sources to improve the performance? Well, there are many options, and on the next few slides, I'll show you just a few examples of designs that have been done to address the weaknesses we've seen here with this architecture. First, let's look at an example that removes the frequency error due to the comparator offset. This approach was first published in ISSCC 2013, and it's one of the many references at the end of this talk that you might find interesting. In this design, the comparator input is chopped such that the impact of noise and current and comparator mismatch is reduced, which you can see in the waveforms at the bottom right. The offset that's present in one phase of the clock cycle makes the frequency slightly too fast. During the next clock cycle, its impact is reversed due to the chopping, which then makes the frequency slightly slower, canceling out the frequency error. Now, in this oscillator, the frequency is given by 1 over 2 RC plus 2 times the comparator delay TD. Chopping has no impact on the comparator delay, so the frequency is still sensitive to any variation in the comparator delay, which might happen due to changes in temperature, supply voltage, or bias currents. And then that sets the lower limit to the power consumption for this architecture. So next, how do we remove the impact of the comparator delay? Well, one option is shown here to the left. There's a ring oscillator made up of two inverters and a capacitor that gets repeatedly charged up, and this then discharges through a resistor. To the right, you can see the voltage on node V1 as a function of time. To remove the impact of any delay variation through the inverters on the frequency stability, they're biased with a voltage V bias that tracks the inverter parameters such that the inverter delay remains constant as temperature and supply voltage change. However, the oscillator is still sensitive to resistor and capacitor temperature coefficients, which means it needs to be designed with passives that have low TCs. And we'll talk more about this in a few slides. The four oscillator examples that we've seen so far were all open loop topologies, where open loop means that there was no feedback around the oscillator itself. We saw an example of a ring oscillator, which was very power efficient but very unstable. Next, we saw three versions of a relaxation oscillator, which were less power efficient but much more stable. So we can improve on these topologies by creating a closed loop topology. In other words, we want to stabilize a ring oscillator by adding feedback around it. This is effectively a frequency lock loop, or an FLL, as shown in the block diagram here to the right. This oscillator architecture can be both very power efficient and very stable at the same time. An implementation is shown to the bottom right. First, we have a power efficient ring oscillator in red with a current source provided in blue. The current source value is set by the output of an amplifier, also in blue, and the ring oscillator clock in orange, which switches a capacitor and a resistor, shown in green. Feedback sets the impedance equal to a reference voltage, which means that the frequency is proportional to 1 over RC. The advantage of this approach is that the feedback loop has a low bandwidth so that the amplifier can have low power consumption. However, the frequency is still sensitive to the resistor and capacitor temperature coefficients. So in all of the oscillators shown so far, the frequency stability, it's a function of the resistor and capacitor TCs. Usually metal capacitors are available in a process node, and they have low variation with temperature, but the resistors may not. One option is to make a composite resistor with resistors having opposite temperature coefficients to approximate a resistor with a 0 temperature coefficient. However, then the resistors have to be trimmed to account for both process variation in the resistance and variation in the temperature coefficient, which leads to a large matrix of switches, which degrades the performance due to their parasitics. So one nice solution to this problem is an oscillator using pulse density modulated resistors, published most recently in 2022. The basic architecture is shown here to the right. There are two resistors that have different temperature coefficients, but unlike the traditional approach, the resistors each only have one switch in series with them. And when the switch is closed, the equivalent resistance is R, and when it's open, the equivalent resistance is infinity. And then by switching each resistor at a different rate versus temperature based on a lookup table from a 2-point trim, the equivalent resistance, and therefore the frequency, can be made relatively constant over temperature, as shown in the plot in the bottom corner. So with all of these techniques, we can remove the impact of many non-idealities in integrated oscillators, leaving us with a frequency that's proportional to 1 over RC. We can even make an equivalent resistor that's constant over temperature. So you would think then that we have a highly stable frequency reference and that all of our problems are solved. However, there's one big issue remaining with these oscillators, and that's frequency drift. The resistors are often made up of p-type polyresistors due to their high density. However, Thermal stress can create traps in the grain boundaries of the poly in the resistor, and that increases the resistance. This resistance shift is logarithmic in time, and it's strongly dependent on temperature. It's possible to see up to 1 to 2% change in frequency just due to this effect over the lifetime of a device if it's operated at high temperatures. This is now the dominant source of error in the state-of-the-art integrated oscillators, and although it's rarely discussed in the literature. Happily, that seems to have changed now, and this year at ISSCC, paper 3.5 proposes a solution to this problem, and I recommend that you check out this paper. So we just saw how oscillator accuracy can be compromised by long-term drift. Long-term stability is quantified by a statistical measurement called Allen deviation, first proposed in 1966. The idea behind this metric is shown in the plot at the bottom left, where the frequency of a clock under test is measured versus a reference clock over different averaging periods of tau. The difference between the successive readings is used to compute the frequency deviation. The Allen deviation is plotted versus the average time, as shown on the plot to the bottom right. A typical plot will cover averaging times from a few milliseconds up to minutes, hours, or even days. There are many characteristic regions of the curve, as shown here, where the Allen deviation is dominated by quantization noise, white noise, flicker noise, bias instability, frequency drift, and so on. The key point of this plot is that the Allen deviation describes how much the frequency varies compared to the nominal frequency over a measurement window tau. Now let's look at an example of why Allen deviation of a frequency reference is really important. So in the plot to the right, the measured Allen deviation of two integrated 32 kilohertz oscillators are shown. Both of the red and the blue curves are from oscillators that have the same power consumption, around 200 nanowatts, and both have similar minimum Allen deviation values of around 3 to 5 parts per million, which is what you can see all the way to the right of the plot here. Now, in many applications, these low power 32 kilohertz oscillators are the only clock available while the system is in a low power sleep state. However, the system is occasionally in a higher power state where a more accurate oscillator is enabled, and during that time, the 32 kilohertz oscillator is recalibrated to the more accurate clock. This technique removes the concern about frequency drift that we just discussed, which is nice. And for these two oscillators, if we assume that we want to calibrate to 100 ppm accuracy, this means that we need to average the blue oscillator's frequency for 1.5 milliseconds. But we need to average the red one for 40 milliseconds to get to that accuracy. This means that the system would need to stay in this high power state for 27 times longer if the red oscillator is used, which would probably drastically increase the average power consumption of the system. The point of this is that the Allen deviation is a critical figure of merit for oscillators, but not just for the floor or the minimum value. We often also care very much about what the Allen deviation is for shorter averaging times. So this slide shows an example use case for an integrated frequency reference. Here we see the block diagram for a wireless system on a chip. It includes a radio, both a receiver and a transmitter to the left over here. It includes a non-volatile memory, a microcontroller, a serial interface, a sensor interface, and a temperature sensor. All of these wireless SoCs use multiple integrated oscillators for their non-radio functions, which are shown in green here. Most commonly, there's going to be a 32 kilohertz oscillator used as an input to a real-time clock for the timekeeping functions. And also there'll be a clock in the megahertz range used for the higher frequency needs. So as mentioned before, these two integrated oscillators are often recalibrated to a more accurate crystal oscillator, shown in blue here, which we will discuss in more detail later. As the final slide in this section, let's look at the state of the art for integrated oscillators published between 2016 and 2023. Since we're considering their use as frequency references, I've plotted the temperature coefficient of frequency, or TCF, in ppm per degree C versus the energy efficiency in picojoules per cycle, because we usually want the most stable oscillator possible using the lowest power consumption. You can see a definite correlation between higher power consumption and lower frequency variation versus temperature. Recent advances in this area include a lower TCF with improved energy efficiency. Another trend is the ability to use two different resistors with the same polarity TC to make an equivalent resistor with a zero temperature coefficient, which is nice because not all technology nodes have a resistor with opposite polarity TCs available. Also, more works have achieved impressive stability with only trim at one temperature point rather than two or more temperatures, which reduces production cost. Finally, as I mentioned before, aging or frequency drift compensation has also been reported in this year's conference for the first time. Now we'll move on to the next category of frequency references, which is oscillators made with ceramic resonators. Ceramic resonators are passive three-terminal devices of piezoelectric ceramic. An example is shown to the right. Their resonance frequency variation over temperature and manufacturing tolerance is typically less than 0.5%. The quality factor is around 1,000, which we'll discuss more on the following slides what that means. They're useful for applications such as microcontrollers that need better accuracy than what's achievable with integrated oscillators over their lifetime, which, as we've seen, can be limited by aging to around 1%. They're also useful to make temperature-compensated oscillators that work over very wide temperature ranges. Oscillators made from ceramic resonators are lower performance, but also lower cost than crystal oscillators, which we will discuss in the section after this one. They're also higher stability, but significantly higher cost than integrated oscillators. Although with the aging compensation techniques introduced this year, they may not compare so well with integrated oscillators in the future. Now let's look at the model used for ceramic resonators, crystals, and many MEMS devices. They can all be modeled by some variant of the four-component modified Butterworth-Van Dyke model topology shown here. LM is the motional inductance, while CM is the motional capacitance, and RM models the loss in the resonator. The term C0 models the parasitic capacitance from the package. The quality factor Q is a function of these three parameters. The resonator appears inductive between the series and parallel resonance frequencies. And also worth noting is that this model has a high impedance at DC, so oscillator topologies need to have a bias voltage defined at each pin. The resonator, whether it's a crystal or a ceramic resonator, has an impedance and a phase versus frequency curves shown as in these plots here, where Fs is the series resonance frequency and Fp is the parallel resonance frequency, which can be written as a function of the resonator model parameters we saw on the previous slide. The quality factor, or Q, is a critical parameter which quantifies how much energy is stored in the resonator versus how much is dissipated per cycle, and the resonance frequency divided by the 3 dB bandwidth. A higher Q means that there's less loss in the resonator and that the impedance peak will be higher and sharper, leading to less energy required to sustain the oscillation, better frequency stability, and lower phase noise, which are all desirable. A higher frequency quality factor also means that the oscillator startup time will be longer, which is usually not desirable. The quality factor of a ceramic resonator is around 1,000, while it's closer to 30,000 for a crystal. This slide shows some example oscillator topologies that can be made with either ceramic resonators or crystals. On the left is a Pierce oscillator. This is a 2-pin structure where the current source supplies a transistor, which is biased by having a feedback resistor between the gate and the drain. A capacitor is added to each pin where the value is specified by the resonator to give the desired oscillation frequency. This topology is very commonly used because it has a pseudo-differential signal on the two pins labeled X1 and X2, which means that you have lower spurs and fewer issues with coupling and the oscillator being pulled by other clocks in the system. On the right is a Colpitts oscillator, which is also commonly used because it has the advantage of only needing one pin to connect the ceramic resonator or the crystal. The other terminal of the resonator is connected to the ground. Here the transistor needs a bias voltage and a bias current, and again, two capacitors are required to match to the resonator. Other topologies also exist, including Butler, modified Butler, clap, and even differential structures, all of which are occasionally used. To end this ceramic resonator section, let's look at an example use case. Here we can see the ADS1255, which is a 30 kilosample per second 24-bit ADC used for scientific instrumentation and industrial process control. It supports 4 to 8 megahertz ceramic resonators or crystals, both of which can be connected to the same on-chip circuit to create an oscillator. The advantage of a ceramic resonator versus a crystal include lower cost, higher reliability, which might be important in some industrial applications, and higher tolerance to electrostatic discharge, and also faster oscillator startup times due to the lower quality factor compared to a crystal. So although ceramic resonators aren't as widely used as they used to be, they still play an important role in some markets. Now let's move on to the next category of frequency references, which are those created with MEMS. MEMS stands for micro-electromechanical systems. They are electromechanical structures that vibrate in the range of kilohertz to gigahertz, depending on their physical size and shape and the way they're fabricated. It's possible for them to have a high quality factor, anywhere from 1,000 to over 100,000, depending on the type. This higher Q enables low power oscillators with low phase noise. A MEMS oscillator is made by combining the micro-electromechanical resonator together with active circuitry, as we saw with the ceramic resonators. However, the difference with MEMS oscillators is that they typically require both active and passive temperature compensation to have sufficiently stable frequencies. With this temperature compensation, it's possible to achieve kilohertz MEMS oscillators with less than 100 ppm frequency variation while consuming less than 3 microwatts. In the gigahertz range, it's possible to achieve less than 20 ppm frequency variation with under 1 milliwatt total power consumption. An advantage of MEMS, unlike ceramic resonators, is that they're very small and they can be co-packaged together with CMOS active circuitry. Also, they're very robust in harsh environments compared to quartz crystal oscillators. So on this slide, there are two examples of 32 kilohertz MEMS resonators, both of which also are included in the list of references at the end of this tutorial. For both of these, the MEMS resonators require fewer mask steps compared to standard CMOS to fabricate. For example, maybe 10 for MEMS versus 30 or more for CMOS, which means that their costs can be relatively low. However, these two examples both require a high drive voltage, meaning greater than 3 volts, to excite the structure into the resonant mode, as shown by VP on the figure to the right. This makes them harder to interface easily with standard CMOS in advanced technology nodes. To adjust the frequency, a tuning voltage is applied, so unlike ceramic structures, these 32 kilohertz MEMS resonators require several more pins. This table shows the status of commercially available low-frequency MEMS resonators. As you can see, there's a limited number of companies producing them, but the performance in terms of frequency stability and power consumption is quite compelling, with a size that's only about a square millimeter, frequency measured in ppm, and current only around a microamp. However, the cost is several times higher than either quartz crystals or ceramic resonators, which limits their use to applications that really value the small size or their robustness in harsh environments. Now, moving up in frequency, let's look at the MEMS resonators available in the megahertz range. Again, I have two examples which are also available in the references list. The first on the left is from SiTime, published in 2017 and is a 47 megahertz resonator in the shape of rings that vibrate in extensional mode. The resonator has the anchors in the center to minimize the losses, which allow the quality factor to be 147,000. On the right is a 167 megahertz MEMS resonator from the Berkeley Sensor and Actuator Center. It's very small with a radius of only 20 microns, but the quality factor at 4,500 is not as high. At the gigahertz frequencies, MEMS resonators are implemented differently from what we saw at kilohertz and megahertz. Instead of structures requiring tuning voltages and a high voltage bias, they're implemented with a piezoelectric material surrounded by electrodes. This piezoelectric material converts between electrical and mechanical energy. Two common types of gigahertz MEMS resonators are SAW and BAW. SAW stands for surface acoustic wave because the mechanical resonance behavior is on the surface of the material. BAW stands for bulk acoustic wave, where the mechanical resonance behavior occurs in the bulk of the material. For BAW resonators, the resonance frequency, FR, is dependent to the first order on the film thickness and the acoustic velocity. In other words, to increase the resonance frequency, the film has to become thinner. And this means that the possible BAW frequencies are set by the thin film manufacturing capabilities. Now let's look a little more in detail about BAW resonators. They're made with Bragg reflectors or acoustic mirrors, which are structures that are alternating high and low acoustic impedance layers that reflect energy back into the piezoelectric film, shown in the middle. The better the mirrors are, the less energy leaks into the substrate or into the package material above, and the higher the Q. The Bragg reflectors also prevent contamination so that the resonator frequency drift versus time, otherwise known as aging that we discussed before, remains low. The dual Bragg structure protects the BAW resonator from moisture and helium contamination, which also makes higher cost vacuum cavities or hermetic packaging unnecessary. In the lower right, you can see a view from the top where the BAW device has been mounted on and wire bonded to a CMOS die. The irregular shape of the resonator is optimized to reduce spurious resonance modes. BAW resonators and oscillators are not new. The first one was published more than 40 years ago, but the BAW resonators have only been used as oscillators in commercial products since 2019. Now let's talk about passive temperature compensation. Many materials used in MEMS resonators expand as temperature increases. The temperature coefficient of frequency, or TCF, is often around -25 ppm per degree C. So uncompensated, this gives more than 3,000 ppm frequency shift over the industrial temperature range, corresponding to the thick black line on the graph. However, silicon dioxide, on the other hand, has a positive temperature coefficient of frequency. If we add a silicon dioxide layer with a perfectly controlled thickness into a MEMS resonator, we can reduce the effective TCF to as low as 0.5 ppm per degree C, corresponding to the blue line on the graph. So the silicon dioxide thickness control, it's the most stringent step in the whole fabrication process of these devices. We have to have really tight control over the thin film thickness. An example of the different frequency variations that you can get for the silicon dioxide thickness being 10 nanometer too thick or too thin are shown in the graph by the green and the purple curves. So manufacturing tolerances are typically not precise enough to add exactly the right thickness of the silicon dioxide. So in reality, we can end up with frequency that varies up to 300 ppm over the entire temperature range. So although the passive temperature compensation of MEMS is really effective, it's still not sufficient to make their frequency reference suitable for all communications protocols. So we saw that a completely uncompensated ball resonator had over 3,000 ppm of frequency variation over temperature. This is much too high for nearly all communication standards. However, we saw that we could add passive temperature compensation through the SiO2 layer, and with precisely the right thickness, we can get down to under 300 ppm frequency variation over the entire temperature range. So that's good, but still not good enough. So what we can do next is combine the passive temperature compensation with active temperature compensation as shown in the diagram here. So we have a temperature sensor that is used to determine the current temperature, and then a lookup table used to apply a frequency correction code to the ball oscillator based on that temperature. So we have active and passive temperature compensation together can get much better results, down to, for example, 20 ppm in this diagram. So the exact clock accuracy will of course be limited by the temperature sensor performance, how often the compensation is done, because it could be done either continuously or periodically depending on the application needs. Designing a gigahertz MEMS-based oscillator has different challenges compared to an integrated LC oscillator that you might be familiar with. As an example, let's look at the complementary differential ball oscillator topology in more detail. On the schematic diagram to the right, the ball resonator is stacked on top of and wire bonded to a base CMOS die. The two NMOS transistors at the bottom are used to provide common mode feedback. A PMOS current source at the top provides bias current. So unlike traditional LC-VCOs, there are 4 modes possible for this ball oscillator. And let's look at them in order of increasing frequency. First, the capacitors CD are added to provide DC decoupling. If they're too small, the oscillator is going to latch. If, on the other hand, the value of CD is too large compared to the equivalent load capacitance CL, we'll end up with a parasitic oscillation. The third mode is the desired oscillation, which is at the loaded resonance frequency of the ball resonator, which for most ball resonators is somewhere in the 2 to 3 gigahertz range due to those thin film manufacturing capabilities we talked about. Finally, there can be a fourth mode where there's a parasitic oscillation that we'll call FB, which is where the bond wires and the equivalent load capacitance from the oscillator CL and the shunt capacitance from the ball resonator C0 form a resonance. So in other words, the design can really be a lot more constrained than your typical 2.5 gigahertz oscillator. If you remember the integrated oscillator discussion earlier in this tutorial, you know that the reference frequency might start out with a very low error at the beginning of life, but that over time it's going to drift as it ages. So one of the issues that delayed ball oscillators from being used in commercial products is that some of the structures were susceptible to contamination. Contamination fundamentally involves particles landing on the resonator, increasing the mass and decreasing the frequency. Conversely, outgassing can occur, which means that the mass decreases and that the frequency increases. An example plot is shown to the right, where the frequency drift is plotted on the y-axis versus time in hours on a log scale on the x-axis, and it's measured while the oscillator was enabled continuously. We see logarithmic aging that happens, which indicates that it could be stress relaxation in the resonator and also CMOS transistor aging. Typically, more frequency drift is seen at higher temperatures, and the important point here is that the frequency drift has to be quantified and included in the total error budget for any frequency reference where the accuracy is important. Another consideration for precision frequency references is how they perform in harsh environments. An example test setup used for mechanical stress testing of a ball oscillator is shown here. The military test standard 833H is used, which requires a peak acceleration of 1500 G with a pulse duration of 500 microseconds on 3 different axes with 5 repeated shocks. Note that the oscillator is kept operational and its instantaneous frequency is measured during these shocks. This slide shows the results of shock testing two SOCs, one using an integrated BAW as the frequency reference, shown on the left in green, and one using an external crystal, shown on the right in red. Instantaneous frequency is plotted on the y-axis versus time on the x-axis. We can see that the integrated BAW shows about 4x better immunity to shock than the external crystal. In other words, about 1 to 2 ppm frequency shift using a BAW versus 4 to 8 ppm for a crystal. This is good news for systems operating in harsh environments, and it's really just due to the BAW resonator having a lower mass than the crystal, so it's less affected by the shock. This sort of testing has to be done for frequency references meant for use in harsh environments, such as factory monitoring, industrial application, and other similar applications. This slide shows an example use case for a gigahertz BAW resonator. It's used to create a reference frequency needed for the PLL in a Bluetooth Low Energy radio. As you can see in the upper right diphoto, the BAW resonator is co-packaged together with the SOC. The BAW resonator has both active and passive temperature compensation, which achieve a frequency accuracy better than plus minus 40 ppm, including frequency drift and aging over a 10-year lifetime, which is sufficient for this radio operation. The advantage of MEMS resonators is their small size, so the PCB space saved by not needing a quartz crystal allows more sensors to be used in the same footprint. Here you can see that in this small space, there's an optical, humidity, and temperature sensor, as well as an accelerometer and an energy harvester. So to summarize the state of the art in the MEMS frequency references, we need to look at them versus frequency. For the gigahertz oscillators, the figure of merit considering the phase noise and power consumption is better than minus 200 dB, and the quality factor of the resonator is greater than 1,000. It's possible to achieve better than plus minus 20 ppm accuracy, including aging with a combination of active and passive temperature compensation. Then for the MEMS references in the megahertz range, we find that the quality factor is greater than 30,000, with plus minus 20 ppm accuracy being achieved with only passive temperature compensation. For the kilohertz references, better than plus minus 100 ppm accuracy can be achieved with only passive temperature compensation again, which then improves to better than plus minus 3 ppm if active temperature compensation is included. So in each case, the package resonator is smaller than 1.5 by 1 square millimeter, while the resonator itself is less than a half a millimeter on a side. So now we'll move on to talk about the fourth type of frequency reference, which is a crystal oscillator. So quartz is a crystalline form of silicon dioxide. If the quartz crystal is cut at precisely the correct angles, an example of that is shown in the figure on the right, then the resonance frequency is very stable over a wide temperature range. So the AT cut, which is 34¼ degrees, is often used for crystals in the 8 to 80 megahertz range, and it gives a characteristic cubic or S-shaped curve for frequency variation over temperature, as shown here. So with this curve, frequency accuracy between plus minus 20 and plus minus 40 parts per million is achievable between minus 40 and 85 degrees C. Another key characteristic of quartz crystals is that the resonance frequency is specified for a given load capacitance. In other words, the crystal might have a resonance frequency of 48 megahertz when it's loaded with a capacitance of 9 picofarad. This is a key parameter because the load capacitance has a very large impact on oscillation power consumption, startup time, and pulling sensitivity. Finally, crystals have to be packaged to be used together with an integrated circuit. The quartz crystal package size is fairly large given that it's a single passive component, with sizes between 1 by 0.8 millimeters and 3.5 to 2.5 millimeters being the most commonly used ones today. Quartz crystals below 1 megahertz are manufactured differently from those in the megahertz range. In the kilohertz range, tuning forks are the dominant quartz crystal shape. You can see a drawing of one on the right of this slide. 32.768 kilohertz is the most common crystal frequency in this range. A tuning fork crystal has a temperature coefficient of frequency that's quadratic, as shown in the bottom right of the slide. This means that the resonance frequency will vary at the temperature extremes, and plus minus 100 ppm from minus 40 to 85 degrees C is typical. Manufacturing variation will cause variation in this TCF, as you can see in the red, green, and the blue lines. And you might wonder why the exact frequency of 32768 is used. Why not 32 kilohertz or 30 kilohertz? The reason is that this frequency is 2 to the 15, which means that a precise 1 second period can be counted with a 15-stage binary counter, which is a low power, low complexity way to implement a real-time clock. So a crystal, together with its active circuitry, which is a sustaining amplifier, form a crystal oscillator. There are several advantages of crystal oscillators. First, it's a mature technology, significantly predating integrated circuits. The crystal oscillator is more than 100 years old, and even though the technology is so old, papers are still being published at ISSCC nearly every single year with advances in crystal oscillators. So this year there are 3. Next, the crystal has a really high quality factor, typically greater than 30,000, which has 2 advantages. First, it enables very low power consumption for the oscillator of less than 10 microwatt per megahertz in commercial products, and in some cases much less. Second, it has a very stable oscillation frequency, as mentioned in the previous 2 slides, with less than 0.01% frequency variation over 100 degrees C. However, despite these advantages, there are some disadvantages as well. First, they're relatively high cost, usually equivalent to 1 to 2 square millimeters of silicon. In other words, this one passive component costs roughly as much as 20 million transistors in a 16 nanometer technology. Also, the size is not small. The most common size today is 2 by 1.6 millimeters squared, and this limits the integration. In the figure, you can see that the 2 crystals are about the same size as the IC. Next, the frequency accuracy, although it's really good, it starts to degrade quickly at the temperature extremes, as we saw in the previous slides. Also, the high quality factor is an advantage for frequency stability, but on the other hand, it means that the startup time is very long, which is a big disadvantage in duty cycled systems. Also, crystals can be sensitive to shock and vibration, and they can fail in harsh environments. They also have frequent supply issues, and under normal circumstances, they have a lead time of 12 to 26 weeks before a manufacturer can get the crystals they've ordered. So on this slide, you can see a classic crystal oscillator architecture, first published by Eric Witos in 1988. Since then, the paper has been cited 243 times in the IEEE papers and 69 times in patents. An important parameter with crystal oscillators is something called negative resistance, which is what enables the oscillator to overcome losses in the crystal from the equivalent series resistance, or ESR. So as a rule of thumb, the negative resistance needs to be more than 5 times the loss in the crystal for the oscillator to start reliably. However, to sustain the oscillation, the negative resistance just needs to be slightly larger than the loss in the crystal. And as you can imagine, a higher negative resistance results in higher power consumption. Therefore, most crystal oscillators have an amplitude control loop to give a higher power at startup and then a lower power in the steady state case. This Witos architecture here is an example of this, and variations of this have been used in billions. The crystal oscillator negative resistance is a function of GM, the transconductance of the sustaining amplifier, the oscillator frequency F, and the load capacitance CL as shown in the equation. We need the negative resistance to be higher than the ESR of the crystal, which is a function of the crystal parameters as shown in the second equation to have robust operation. We can see from these equations that we want a high transconductance for robust operation, but we usually also want low current consumption. We can calculate the minimum current consumption needed for a continuously biased sustaining amplifier by assuming that the transistors are biased in the maximum GM over I point, where the GM equals current divided by the subthreshold slope factor and the thermal voltage. However, it's important to note here that the negative resistance is a strong function of the load capacitance CL. So if the load capacitance is not specified, you can't evaluate how competitive the current consumption is. Frequency tuning for a crystal oscillator is done by adjusting the capacitance loading on the crystal. In this example, we have two capacitors, C1 and C2 on each side of the crystal, such that the equivalent load is the series combination of the two. If the two capacitors are equal, which they often are, then the load is 1/2 of C1 or 1/2 of C2. To get the correct oscillation frequency, the equivalent load capacitance has to match the value in the crystal specification. If it's too low, then the oscillation frequency is too high, and if the load capacitance is too high, then the oscillation frequency is too low. If you have an oscillator where the frequency is wrong, you can calculate the error in the load capacitance by using the frequency tuning equations shown on this slide. Another important crystal oscillator metric, especially in duty-cycled systems, is the startup time. For a traditional architecture with a continuously biased sustaining amplifier, the startup time constant tau is a function of the loss in the crystal and the crystal motional inductance, capacitance, and the amplifier negative resistance, as shown in the equation for tau here. A stable amplitude takes 7 to 15 time constants. Example parameters from two different 24 MHz crystals are shown in this table. The one in a larger package has a lower motional inductance and therefore a faster startup time. A second in a smaller package has a much larger motional inductance and a longer startup time and will therefore take more energy to start up, which can be a disadvantage in duty-cycled systems. So you might ask, why would you choose the second crystal? Well, one reason is that the pulling sensitivity is better, or lower, for crystals with larger motional inductance. Pulling sensitivity is a measure of how much the frequency changes if the load capacitance changes, which can happen due to environmental change. So there's a trade-off between startup time and frequency stability. The crystals that take longer to start have a frequency that's less sensitive to changes in the environment. So crystal parameters are impacted by package size. As the package size is reduced, the series resistance, which is the loss in the crystal, increases. Also, the motional inductance tends to increase. Both of these changes cause slower crystal oscillator startup time, which means more energy is required each time the crystal oscillator starts up. The lowest cost crystal size is the one used in the cell phone market due to the volumes, and that size drops over time. So if we do nothing, this means each new generation of designs would have increasing power consumption, which is obviously not acceptable. So one solution to this problem is to kickstart the crystal oscillator with another integrated oscillator at a frequency that's very close to the crystal resonance frequency. It's important, though, that the startup time reduction is robust and repeatable. Many systems have to assume the worst case crystal oscillator startup time. So if you have one that starts up quickly only sometimes, it's not useful. So there are various ways to do this that have been published over the last 5 to 10 years, but all have the same goal, a lower startup energy for the oscillator. So this slide shows some examples of techniques that have been used over the last 35 years to get faster oscillator startup time. You can see a detailed list of references in Lee's paper in TCAS2 from 2021. First, the technique proposed by Vitas in 1988 can be used, which just provides a higher bias current to the oscillator on initial startup, then reduces it during the steady state. This works, but it has a limit to how effective it is. Second, a lower load capacitance can be used. This makes the oscillator frequency more sensitive to environmental changes, though. Third, a higher frequency crystal can have a faster startup time, but then the steady state power consumption is also higher, so it's not a net benefit. Fourth, a chirp frequency can be injected into the crystal. This is simple, but it has limited effectiveness. Fifth, a tone within about 0.5% of the crystal frequency can be injected. This is very effective, but it requires a second precise oscillator. Sixth, self-time injection can be used. This requires a peak detector, but gets extremely good results. Seventh, injection using a phase error detection can be used. This is effective, but requires an accurate oscillator at a much higher frequency than the crystal. This is not a complete list, but you can see that the community has been very active in the recent years trying to solve this problem. You might wonder, given the increase in the size and the extra complexity required to achieve a fast startup time, why crystal oscillators are so widely used. Well, one of the main reasons is the low phase noise that they can achieve, which is necessary for many communications and high data rate applications. Phase noise is the ratio of noise power to the power of the carrier, or the fundamental signal. It's a frequency domain representation of noise. An example phase noise plot is shown to the right, where the x-axis is frequency and the y-axis is the signal normalized to 0 dB. Units for phase noise are in dBc per hertz, and it's referred to an offset frequency. So in this plot, an example would be that the phase noise is minus 80 dB at 100 kilohertz offset, as shown by the red dot. Crystal oscillators can achieve quite low phase noise at the same time that they have a stable, accurate frequency due to the high Q resonator. Compare this to an oscillator with a low quality factor, such as an integrated oscillator, and you can see how much higher the noise can be in the example orange plot. So here the energy is spread out over a wider frequency range, meaning that it's less stable. So in some applications, the crystal oscillator noise will be specified with jitter instead of phase noise. Jitter is fundamentally the deviation in time of the clock edge from the ideal time. There are several jitter metrics which can be used depending on what's important for the system. First, cycle-to-cycle jitter, which is the deviation of the period from one clock cycle to the next, which is particularly relevant for digital circuits to ensure timing constraints are met. Next is period jitter, which is how much any period varies from the ideal value, also important for the digital circuits. Third, we have a long-term jitter or end-cycle jitter or cumulated jitter, which is the deviation in multiple cycles from the average value. And fourth, we have integrated jitter, which is the phase noise integrated over a specific bandwidth, frequency bandwidth and converted to jitter as shown in the equation here. This is relevant for wireless applications, PLLs, and high-speed serial links. 2 slides ago, we saw how much lower phase noise and therefore also lower jitter a crystal oscillator has compared to an integrated oscillator. The long-term stability of crystal oscillators measured by the Allen deviation metric is also much better than integrated oscillators. An example is shown here, and where this slide has measured Allen deviation with averaging time between 1 millisecond and more than 10 seconds for 232 kilohertz oscillators, both of which consume about the same current, around a few hundred nanowatts. The integrated oscillator is based on an RC network and has no external components, while the crystal oscillator requires that external quartz crystal. You can see that the crystal oscillator achieves much lower Allen deviation, particularly at the long averaging times, than the RC oscillator does. So just like the improved phase noise, this is fundamentally because of the high quality factor of the crystal. So even though crystal oscillators were first built more than 100 years ago, there are still new improved variants proposed every year. An example presented at the IEEE Solid State Circuits Conference in 2014 is shown here. So instead of having a continuously biased sustaining oscillator, as we've discussed before, the energy is only supplied in this circuit to the crystal in short bursts. The idea here is that when the two differential signals on the crystal pins are at the same value in a traditional crystal oscillator, the bias current just goes straight through the amplifier and doesn't do anything to sustain the oscillation. On the other hand, when the signals are at the maximum or minimum values, energy gets injected into the crystal. So in this architecture, the bias current is supplied to the oscillation only at the extremes, greatly reducing the power consumption to just under 2 nanowatts compared to a typical design that might consume 100 nanowatts or more. So crystal oscillators are very popular due to their combination of high stability, low phase noise, and low power consumption. However, these advantages don't come for free. Crystal oscillators can have many failure modes. This slide lists just a few examples of them. First, most crystal oscillators are meant to operate in the fundamental mode, but it's possible to have too much gain at a high frequency in the sustaining amplifier and then get an oscillation at an overtone. You can see in the example crystal reactance plot versus frequency shown to the right, with clearly visible peaks at the third and the fifth overtones. Crystals can have not only overtones, but also spurious modes, which can degrade the phase noise. Similar to this, they can have activity dips, which is when resistance suddenly increases at a certain temperature due to interference modes of the vibration. Next, crystal oscillators, particularly 32 kilohertz ones, can fail to oscillate due to high humidity, causing a low impedance between the pins. The crystals can actually break if they're subjected to too much shock. And finally, startup problems are quite common as well and can take a lot of different forms, sometimes due to the fast startup features not working as desired. So crystal oscillators are extremely widely used in electronics, so there are many possible example use cases I could show you. The one I've chosen to here is a Wi-Fi network processor with a 40 megahertz crystal oscillator. Wi-Fi has very strict requirements on the frequency accuracy and the phase noise for the crystal oscillator, and they're determined by both RF regulatory requirements and the Wi-Fi standard. First, the phase noise needs to be below minus 125 dBc hertz at 1 kilohertz offset and falling to minus 143 dBc per hertz at 100 kilohertz offset. The frequency needs to be accurate to better than plus minus 20 ppm over the operating temperature range. And finally, the frequency drift needs to be less than 0.16 parts per million per millisecond. This last specification is challenging for a crystal oscillator when there's an on-chip power amplifier due to self-heating. So this is an example of where a more stable oscillator might be needed, which is what we're going to talk about in the next section. So now I'll summarize the state of the art for crystal oscillator designs. For megahertz oscillators, the startup time is between 100 to 1,000 cycles, which is 10 to 1,000x improvement over the traditional design that was common around 10 years ago. The megahertz oscillator power consumption for a state-of-the-art design used in a commercial product is 1 to 2 microwatt per megahertz. It's important to note here that the power is strongly dependent on the crystal parameters and the phase noise specification, so you'll see an extremely wide variation in this power consumption that's reported in the literature. For 32 kilohertz oscillator power consumption, the state-of-the-art is around a nanowatt versus around 100 to 200 nanowatts for traditional design. For both megahertz and kilohertz oscillators, the silicon area state-of-the-art is around 0.03 square millimeters, which includes area for the load capacitance. Again, this is dependent on the crystal parameters and the technology node used for the design. So the next category of frequency references are the temperature compensated crystal oscillators, or TCXOs, and the oven compensated crystal oscillators, or OCXOs. So the first type of TCXO is a crystal oscillator where the temperature compensation is implemented in software. Megahertz crystals, when considering manufacturing tolerances, can have more than 50 ppm frequency variation over extended temperature ranges, as you can see in this plot here in the upper corner. This is too much for any wireless application using a narrow channel bandwidth, or GPS, for example. So one solution to this is to implement a TCXO in software as shown at the bottom left. Firmware or software computes the estimated crystal frequency error based on inputs from a temperature sensor, some stored fitting parameters and coefficients, and a stored room temperature frequency measurement. Then the adjustment is applied to the PLL or a frequency synthesizer, giving a compensated frequency at RF for a radio to use. In the bottom right, you can see measured results from this technique, reducing the error to less than 10 ppm and giving a quite accurate frequency. In some applications, though, the 10 ppm stability over a wide temperature range that we saw on the previous slide is still not sufficient. So in these cases, we need to use a TCXO where the crystal oscillator and the compensation circuitry are all packaged together. The classical TCXO implementation is shown in the diagram at the top, where the temperature sensitive reactance, shown by the blue box, is used to counteract the natural temperature coefficient of the crystal in red, which you can also see in the red curve, giving a stable frequency, which you can see in the green curve. This compensation approach that's shown here is done in analog, but there are also digital TCXO versions of this. So compared to crystals, TCXOs cost about 3 times more, but they have 10 to 20 times better stability versus temperature. The power consumption tends to be around 4 times higher, and the startup time can be about 4 times longer. So you can see that TCXOs are only going to be used where the frequency stability requirements really demand it. So TCXOs can have either analog or digital temperature compensation, and they can also be implemented with 2 different output clock types. The first is called a clip sine, as shown by the top schematic. The advantage of this type is that it has lower spur level than the rail-to-rail output type, which is especially useful for wireless applications. The disadvantage is that it requires coupling capacitors and an on-chip buffer that has to have its own bias to convert an input square wave to an input square wave on the receiving chip. The second type is called a CMOS output TCXO, which just means that the output is a rail-to-rail signal. The disadvantage here is that the large swing can cause spur issues, and also the TCXO supply now has to be equal to the supply on the receiving side, but the advantage is that no coupling capacitor or special input buffers are required. So if you specify TCXOs for a project, it's important to be aware of these 2 types because they're not interchangeable. So this slide shows an example use case for a TCXO. Internet of Things standards with narrow RF bandwidths require the radio to use a very stable reference clock, often with all error sources adding to less than 10 parts per million. An example is a 900 megahertz carrier transmitting data with a 5 kilohertz deviation that has to be received by a low power battery operated radio, as shown in the figure. In the plot on the right, the receiver packet error rate is plotted versus the error in the reference frequency used by the RF synthesizer, which is swept between -15 to +15 ppm. So the black indicates that the error rate has approached 100%. So this plot shows that the receiver sensitivity degrades beyond a frequency error of about ±10 ppm. So crystal oscillators used by low power radios typically have an accuracy of 10 ppm just at room temperature. So once the temperature varies, the frequency variation will increase, and that means that these narrowband systems require a TCXO. For some specifications, such as a network clock synchronization, radar, instrumentation, even the stability achieved with a TCXO is not sufficient. So in these cases, an oven-controlled crystal oscillator, or OCXO, can be used. In the crystal oscillators we discussed earlier, the AT-cut crystal was most commonly used for the megahertz frequencies, which gives a frequency versus temperature curve that's a cubic, as shown by the red curve on the plot. However, it's also possible to cut the quartz crystals in a shape called the SC cut, which gives the curve shown in blue. So obviously the blue curve has worse performance at colder temperatures. However, at the higher temperatures, it's much more stable. So an OCXO is then an SC cut crystal oscillator placed inside of an oven that's heated to a constant temperature somewhere between 80 and 100 degrees C, as shown in the block diagram below. So typical OCXO specifications are a package size of up to 70 by 38 millimeters squared and a frequency stability between 200 parts per billion and a warm-up time stabilization time of about a minute and a power consumption between 1 and 4 watts, depending on the ambient temperature. So very good results are possible, but at significantly higher power consumption than any frequency reference we've discussed earlier in this talk. So now that we've reached the last section of frequency references that I'm going to introduce today, and that is the atomic clocks, particularly the chip scale atomic clocks. So atomic clocks are different from the frequency references presented so far. The previous oscillators have had their frequencies determined by the properties of some fabricated object, such as the sheet resistance of a polyresistor, the size and shape of a MEMS resonator, or the dimensions of a quartz crystal. Atomic clocks, on the other hand, have their frequency determined by the resonant frequency of atoms, which is a physical constant. The block diagram of an atomic clock is shown at the bottom right, where there's something called a physics cell. And this physics cell has atoms that are excited by a frequency F0, which cause the electrons to transition between different energy levels. There's a detector that detects this electron transition, and the feedback loop adjusts F0 so that the maximum amount of electrons transition. And then F0 is set by the atom used in the physics cell. So two commonly used ones are rubidium, with F0 equal to 6.8 gigahertz, and cesium with F0 equal to 9.2 gigahertz. So unlike the other clock sources we've discussed, most atomic clocks are quite large and they consume many watts of power. Atomic clocks are also a huge topic in and of themselves, so I'm just going to touch briefly on the chip scale atomic clocks in this tutorial, which are a more recent develop in this space. So chip scale atomic clocks were first demonstrated about 20 years ago, and they went into production just over 10 years ago. They work by having cesium atoms inside of a physics cell, which are heated to produce a gas, and then a laser excites the cesium, and the electron transition is measured by a photodetector. So the images to the right show the Microsemi SA45S chip scale atomic clock. So unlike traditional atomic clocks, the power consumption is really quite low at only 120 milliwatts. Aging is less than 10 parts per billion per year, and the Allen deviation is 10 to the minus 11 over a 1,000-second measurement window. So it weighs only 35 grams and has a volume of less than 17 cubic centimeters. The public price as of last fall is around $2,600 US. So now let's look at a frequency reference use case that requires the precision available only from an atomic clock. So one example is undersea sensing used for oil exploration. So reflection seismology is shown in the diagram to the right, where there's an array of sensors on the ocean floor which measure reflection from a sonic pulse sent from a ship on the ocean surface. So the data from the sensors is post-processed and it's used to map the layers beneath the ocean floor. And as you can imagine, the timing accuracy determines the mapping accuracy. So the chip scale atomic clocks have lower power consumption, yet even better frequency accuracy than OCXOs. So they are ideal for this use case. The chip scale atomic clocks enable longer lifetime on the same size battery, and then more accurate sensors can be deployed, enabling more data to be collected and more accurate maps. So that brings us to the end of the different types of frequency references. So now we'll go to the summary and the conclusions. This plot shows a comparison of the Allen deviation for 4 different types of frequency references that we've discussed. So on the y-axis is the frequency deviation plotted on a log scale. So it's between 0.1% at the top to much less than 1 part per trillion at the minimum. On the x-axis is the averaging time window over which the measurement was done, also on a log scale, from a millisecond to more than a month. So for each type of oscillator, there's a box showing where the typical Allen deviation results will be. You can see that the integrated RC oscillators are at the top in blue, and then several orders of magnitude below them are the crystal oscillators in red. And then several orders of magnitude below that are the Allen deviation for the rubidium and cesium atomic clocks. You can see that although the Allen deviation floor occurs at different averaging times for each of the oscillator types, the basic shape is the same, of first decreasing and then as the averaging time increases, flattening out and then rising again. So this table shows the high-level comparison of the typical values from the 7 different types of frequency reference that we've discussed today, from the integrated silicon references to the atomic clocks. Each row is color-coded, with red showing the worst or highest parameter, and green showing the best or smallest parameter. In the first row, you can see that the integrated oscillators are very flexible, supporting frequencies from hertz to gigahertz, while some of the other types of those based on crystals are more limited to their fundamental frequencies. Next, the physical size is compared, and it varies over 8 orders of magnitude. The third row compares frequency stability, and here there's even more variation with around 13 orders of magnitude between the integrated frequency references and the atomic clocks. Not surprisingly, the power consumption goes in the reverse direction, with the most stable frequency references requiring the highest power consumption. Finally, typical cost is compared as well, with the integrated oscillators costing a very small fraction of a US cent, while the atomic clocks cost thousands of dollars. So in summary, I hope this tutorial has given you a solid overview of the wide field of frequency references. So in conclusion, nearly every electronic system needs a clock, and although we see that the accuracy and cost and power requirements can vary tremendously. Because of this, many different types of frequency references have been developed, including silicon integrated oscillators, ceramic, MEMS, and crystal oscillators, temperature compensated and oven compensated crystal oscillators, and chip scale atomic clocks. So during this tutorial, we've looked at each of these types of references and seen that they have a wide spectrum of performance, spanning 8 orders of magnitude in power consumption, around 14 orders of magnitude in frequency stability, and so on. And despite this wide variation, though, the fundamental concepts we've discussed are applicable to all of them. And I hope you've gained an appreciation of this interesting and extremely relevant field. Finally, let me suggest some papers that you should see this year at ISSCC. In the integrated oscillator category, there are 2 papers this year at ISSCC on RC oscillators. The second one, paper 3.5, addresses the problem of frequency shift in RC oscillators and achieves about 0.1% accuracy, even including accelerated aging at 125 degrees C. This paper is the first addressing this problem, so I encourage you to check it out. Then there are 2 papers on megahertz crystal oscillators with new techniques to get faster startup time. Paper 3.8 is a low-frequency crystal oscillator with power consumption under a nanowatt. And finally, paper 3.9 is a BAW oscillator with a fractional output divider achieving less than 95 femtosecond jitter. So as you can see, the frequency references are a key topic with 6 different papers on it this year at ISSCC. That brings me to the end of the tutorial, and the remaining few slides are key references, which I encourage you to read if there's a particular topic you're interested. Thank you for your attention.